In this lesson, we're going to look at theoretical probability. You may remember in the last lesson we looked at experimental probability. And so these are both measuring the same thing. They're measuring the likelihood of something happening, but they're doing it two different ways. So you may recall that experimental probability was based on trials. You do a certain number of trials, and then the number of successes you get divided by the number of trials gives you experimental probability. And successes could be anything. It's whatever you're trying to measure. But the key idea for experimental probability is that you have to actually do an experiment, or the world has to do an experiment for you. You don't have to be the one setting it up. It could be something that happens in nature, but it's still just based on actually counting things that have happened. Theoretical probability is not based on doing things. It's based on thinking about them. It's based on counting up the possible outcomes. So here's the formula here. And it is very similar looking to experimental probability. It still has P at A, so the probability of event A happening. So this big A, remember, is the event. It's what you're measuring. It does have N of A as well. In experimental probability, let's just go back for a second actually and take a look at that because it's good to compare. So yes, we had N of A, number of successes. We had P of A, which is the probability of event A happening. And we had N of T, which was the number of trials. All right, so let's now look at, well, let me circle this one too, just so that it stands out. Okay, so that's the formula. The one we're about to go to looks exactly the same, except on the denominator it says S instead of T. And the reason it says S on the denominator, N of S, is because we're not measuring the number of trials, we're measuring the number of possible outcomes in something called the sample space. So the sample space, if we think about it in terms of a Venn diagram, remember Venn diagrams from elementary school? Let's see, let's draw a nice Venn diagram. So if you got some sort of box, and then inside the box we put some circles. Let's get another one and overlap them. Okay, so this is a classic kind of Venn diagram. And the box represents everything. And we call that the sample space. And what's inside the box are specific events. We've already talked about an event A, but we could have an event B and an event C. And sometimes these two events overlap even. So maybe event A is it raining outside today. And maybe event B is, let's say you decide, or someone's going to play football. So like there's a team that you look out your window every day, and some days there's football and some days there isn't. That's just what came to me as an example. So event A would be every time that it's rainy. Event B is every time people play football. And they're not related to each other, but we could count up the possible ways that could happen, and they could even overlap, right? So people could play football when it's raining, they could play football when it's not raining, and all those go into different places on the Venn diagram. I'm not going to get into that right now because we're going to talk about Venn diagrams later. All we really need to know for now is this idea of the sample space just being all the possible outcomes. Okay? That's what sample space is. So I'm going to write it again here. And draw an arrow. So, sample space. Except I didn't write it very neatly, did I? Sample space. All right. So, N of A in experimental probability was the number of successes, the number of times something happened. But N of A in theoretical probability, since we're not actually doing trials, is the number of ways it could happen. So the number of possible successful outcomes. So the emphasis on success is still low, right? Where N of S is all possible outcomes. So whether it's counted as a success or not, it's just all the ways that something can happen in the sample space. So the sample space collection of all possible outcomes, sometimes called the sample set. An event is the set of all outcomes that have a common characteristic, so it's what we're measuring, right? So for example, maybe our event is rolling a six-sided die. Sorry, that would be our experiment. Backtrack for a second, because our event is what we're looking for. Apologies. That's our experiment from before. And our event would be what we're measuring. So if I roll a six-sided die, maybe what I'm looking for is even numbers, or the probability of rolling an even number. And the sample space would be all sides of the die, all the outcomes. So if I want to put that in just common English, I roll a die, and I'm interested to know what's the probability of rolling an even number. Well, the probability of rolling an even number would be the number of ways of being successful. Well, there's a 2, a 4, and a 6. So there's three successful outcomes, divided by all the outcomes, whether they're successful or not. And on a six-sided die, there would be 6. So it would be 3 over 6. The theoretical probability of an event occurring is the measure of its likelihood based on analysis of all possible outcomes, as I just said. Theoretical probability of an event is calculated by dividing the total number of favorable outcomes by the total number of outcomes in the sample space. So, for example 1, determine the theoretical probability of rolling a standard die and it turns up 3. Okay, so let's call that event A. So event A is rolling a 3 on a six-sided die. And so the probability of rolling a 3, probability of event A, is N of A, number of ways of rolling a 3. So N of A, I'll just do this over here. There's one way to roll a 3 on a six-sided die, divided by the total number of possible outcomes, N of S. So the sample space, you could roll a 1, 2, 3, 4, 5, or 6. There's 6 outcomes. So the probability of rolling a 3 is 1 over 6. Determine the theoretical probability of drawing a card at random from a standard deck of cards and it's an ace. So we'll call that event B just to give it a different name. And drawing an ace. And let's just do it here, N of B, number of ways of drawing an ace. If you've played cards, you'll know that there's 4 aces in a deck. And you'll also know that the sample space is all the cards in the deck, and there's 52 cards in the deck. So the probability of drawing an ace is N of B, which is 4, over N of S, which is 52. And then, of course, as we saw in a previous lesson, we always reduce. So that's equal to 1 over 13. Determine the theoretical probability of flipping a coin 3 times and getting exactly 2 heads. All right. Well, let's call that event C. 2 heads on 3 flips. Now this one gets a little bit trickier, and that's the interesting thing about probability, is we got these really simple probability ones like we just saw in example 1 and 2, but probability can quickly get a lot more confusing. I don't know if you have an intuitive sense, a subjective sense of what the probability of getting exactly 2 out of 3 heads on 3 coin flips is, but let's use a really good tool that we're going to come back to a lot in this course, a tree diagram, to help us sort this out. So if we were to flip a coin one time, there's only 2 possible outcomes. You could get heads or you could get tails, right? That's flip 1. If I got heads on the first flip and then I flip again, I can still get heads or tails, of course, on the second flip. And the same thing goes for if I got a tails on the first flip. If I flip again, I could still get heads or tails. So far I've imagined flipping a coin twice, and there's actually 4 possible outcomes. Let's take a look at them. It could go heads, heads, so I could get 2 heads on 2 flips. I could get a heads followed by a tails on 2 flips. I could get a tails followed by a heads on 2 flips. Or I could get both tails on 2 flips. Notice how I just highlighted 4 different paths. 1, 2, 3, 4 different paths, and each path is an outcome. So there's actually 4 outcomes if I flip 2 coins. However, this one wasn't about flipping 2 coins, this is about flipping 3 coins, which means that no matter what's happened so far, I'm still going to have an opportunity to get a heads or a tails on the third flip. So on flip 3, if you count up the number of paths like I just did for 2 flips, what you'll see is there's actually 8 different paths. So there's 8 paths altogether. That would be our N of S. That's our sample space. So for example, just to randomly pick one, say I do this path that I just highlighted in yellow. That path involves getting a heads followed by a tails followed by another heads. That's the only, that can only happen on that path. There's no other path that's exactly the same combination of heads and tails. If I randomly picked a different path, say I picked this one, that would be tails followed by heads and then another heads. So each path is a different outcome. So there's 8 outcomes. We want the paths that contain exactly 2 heads. Not 2 or more, we want exactly 2 heads. So we have to just go down the paths that have 2 heads and 1 tail, since that has to be their option, but they can be in any order. So it could go heads, heads, tails. It could go heads, tails, heads. Or it could go tails, heads, heads. If you look at the other 5 remaining paths, none of them have exactly 2 heads on them. So we can't count those as successes. So there's 3 ways of getting exactly 2 heads. So it turns out the probability of getting exactly 2 heads on 3 flips is 3/8. The complement of a set of outcomes not include, I was reading that wrong. The complement, what the complement is the set of outcomes not included in an event A. And we denote that as A prime, okay? So that's read as, so it's A with an apostrophe, or an apostrophe beside it, or a B or C or whatever, but it's read as A prime. That's how we say it. So when I talk about A prime, you'll picture A with an apostrophe beside it. And so it's the complement. So the complement is the outcomes not included in event A. If we go back to example 3, the probability of getting 2 heads we saw was 3/8. And we represented the the event as event C. So C prime, let's see, let's draw it up here. So C prime from this example is probability of not getting exactly 2 heads. So it's getting anything else, right? So getting 3 heads, getting 1 heads, getting 0 heads, those are all the different paths that we didn't include in example 3. The thing about complements and the event that the complement of is that probability adds up to 100%, right? Because again, all probabilities have to add up to 100%. So if we have a probability of 3/8 of getting event C, of getting 2 heads, the probability of the complement, let's do it up here, so the probability of C prime of not getting exactly 2 heads, of getting anything except 2 heads, would be 1 minus 3/8, which is 5/8. 3/8 plus 5/8 equals 100%, or 1. So I'm just referring to this formula here. That's not a nice way to highlight it, is it? Let's circle it instead. There we kind of go. Don't like that either. All right, I'm going to zoom in and circle it, because that's an important formula. It's a very easy formula. As you're going to see, some formulas in this course are really easy, but we still need to know them. So that's the complement formula. The probability of the complement of an event is the probability that the event will not occur. Okay? That's another way of saying it. So if the event is getting 2 heads on 3 flips, the complement is not getting 2 heads on 3 flips. And again, there's 5/8 probability of that. So let's look at an example that helps illustrate this. Battleship is a game in which 2 opponents use a coordinate grid to try and guess the location of each other's ships. What's the theoretical probability of hitting a ship on the first guess? Well, the board is 10 by 10. So, let's call this event A, hitting a ship. And n of s, the entire sample space, the board is 10 by 10. So there's 100 different squares that you could select. If we count up the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 spots that you could hit, that's n of A. So the probability of hitting a ship on your first guess is 17 over 100, or 17%, or 0.17. What's the probability of missing on your first guess? Well, probability of missing would be the complement, right? So the probability of missing is the probability of A prime, which is 1 minus 0.17. So we have a probability of 0.83, or 83% of missing on our first guess. Now, the last thing I want to talk about today is something called odds. So, pay close attention, because odds are not the same thing as probability. I'm going to say that again, because a lot of people confuse odds and probability and treat them like they're the same thing. Odds is not the same as probability. Probability is a mathematical calculation for whether something's going to happen. So probability of hitting a ship on your first guess, we work it out as 17 over 100. We can express it as a percent. Odds instead is the ratio that a probability ratio of the probability that an event will happen to the probability that it will not happen. So instead of comparing as we did, let's go back to this again. What we compared here was comparing number of successes, ways to be successful, to total number of ways of doing things. That's probability. Odds compares the probability of being successful to the probability of being unsuccessful, is another way of thinking about it, or even just probability of an event to its complement. So this is a kind of a simple formula. So let's again go back to Battleship. We have a 17% or 0.17 probability of hitting a ship on our first guess. But the odds of hitting a ship on our first guess is not 0.17. It would be 0.17. So odds of success compared, we usually use a colon to compare it, to the odds of failure. Now, having it as decimals is very awkward. We should maybe compare them as percents, would be a nice way to do it, except I don't need to actually write a percent symbol down. So it could be 17 to 83. It can be like a fraction, except it's in reduced form. So instead of saying 17 out of 100, I'm saying 17 to 83. So if I give the odds as 17 to 83, I'm saying that there is 17 chances of success compared to 83 chances of failure for hitting a ship on my first guess. Now I could reduce that. 17 goes into 83. It doesn't go in evenly, but it's close to going in 5 times. That's approximately equal to 1 to 5. So I'd have about 1 chance of success for every 5 chances of failure when I'm guessing at where a ship is in Battleship. Let's look at another one. A racehorse has a subjective probability of 65% that it will win the next race. What are the odds in favor of this happening? Okay, so if we say event A is the horse winning the next race, and we're told that P of A equals 65%, that means that the complement, probability of the complement, would be 35%, right? We had that formula of 1, where is it? 1 minus the probability of A, or if I'm doing it as percents, it would be 100% minus the 65%. Again, probabilities have to add up to 100% as percents, or add up to 1 if you have them as decimals or fractions. But anyway, so the probability of success is 65%. The probability of failure, the complement, is 35%. Therefore, the odds, again, are the ratio of success to failure, 65 to 35. But, again, these ratios, just like fractions, should be reduced. I can divide both sides by 5, and I'd get 13 to 7, and that would be a reduced ratio. So it's approximately twice as likely to win its next race as it is to lose.